Hi everyone. In this video we're going to introduce mass spectrometry, which is an analytical technique that we can use to try to figure out the structure of an unknown molecule. So down below you can see a diagram for a traditional mass spectrometer. So essentially how a mass spectrometer works is you introduce your sample to the instrument, and then it travels through and is hit with a beam of electrons. Now, once your sample is hit with that beam of electrons, that's going to turn your molecules into ions. So this is called the ionizing region. Then the ions are accelerated through a magnet, and depending on the ion's mass and charge, it will be deflected and hit a detector. And then once your sample has run through the system, a computer will convert the detector's data into a mass spectrum. Okay, so let's talk a little bit more about the ionizing portion of the instrument. So let's say you have a carbon-carbon bond in a molecule. And remember that a covalent bond is 2 electrons. If we hit that with an electron beam, so it's really just a laser of electrons essentially, you end up knocking off one of the electrons or removing one of the electrons. So now there's only one electron sitting in between those carbons. So that means that this molecule is now positively charged because it's missing an electron. And it's also a radical because it only has a single electron there in between the carbons. So we call this a radical cation. And that will be important later. Now, what can happen next is that single electron can move to one of the carbons, and we end up forming a carbocation and a radical. Now, mass spectrometers can only detect charged particles. They can't detect just a simple radical. They can detect a radical cation because it does have a charge. But if something doesn't have a charge, if it's neutral, then the mass spectrometer cannot detect it. So let's just make a note of that. All right. So earlier I said that once the ions pass through the magnet, they can be deflected. So let's just kind of draw what that looks like. So let's say we have our ion and we have our magnets, and we'll just draw these as plus and minus. So an ion can pass through and be deflected by the magnet or the electric field, whichever one you're using. And then it will hit the detector at the end of the instrument. So the detector again measures deflection from the central point here. So the difference is the deflection of the ion. Now the deflection of the ion depends on its mass, its charge, and the strength of the magnetic field. So let's actually write that on the next slide. All right, so deflection of an ion in a magnetic field depends on, oops, I can't write and talk at the same time apparently. One, the mass of the ion, two, the charge, and three, the strength of the magnetic field. And these are listed in no particular order. Okay, so let's say that you run a sample and your ions are deflected by the magnet, and then the detector detects the ions. What you end up reading is a mass to charge ratio. So mass spectrometers measure a mass to charge ratio for an ion / compound. So mass is given the symbol m, which makes sense, and charge is given the symbol z. So the mass to charge ratio is m over z, or mass over charge. So for example, let's say the mass of your compound is 100. And let's say you ionize the sample in the mass spectrometer and its charge is +1. Then the mass to charge ratio would be 100 over 1, which is just 100. Or let's say that the mass is 100 and maybe the charge ends up as +2, then the mass to charge ratio will be 100 over 2, or 50. Now, for our purposes, we're just going to assume that the charge is +1 for each of our ions. It will make things a little bit simpler. So now let's talk about how to analyze a mass spectrum. So down below in figure A, we have a mass spectrum for methane. So on the y-axis, we have relative abundance. So this is going to tell us how abundant each ion is. And on the x-axis, we have the mass to charge ratio. Okay. Now, remember from earlier, we said that we can end up with a radical cation after a molecule is hit with a beam of electrons. So we use this symbol to indicate that we have our radical cation. So it's just a capital M in parentheses with a plus sign and a little dot for the electron. Now, we're also going to call this our parent peak. So, remember earlier we drew this example where we had our starting material, and then after it was hit with electrons, we had the radical cation. So this radical cation has only lost one electron. And remember, electrons have negligible mass. So the mass is really, really small, which means that the mass of our starting material is approximately the same as the mass of our radical cation. So if we can find the peak for the radical cation, then we can figure out the mass of our original compound, which is super useful. If you know the mass of the starting material, that can help you kind of narrow down what compound you have. So let's talk about how to find that peak, that parent peak, which is the radical cation peak. So looking down below at the mass spectrum, the tallest peak in this cluster of peaks is at 16. So an m over z of 16. So that will be our parent peak. Now, sometimes you'll have multiple clusters of peaks. So what you're really looking for is the tallest peak in the rightmost cluster. So look for the tallest peak in the rightmost cluster. So the cluster that's furthest to the right. Now, again, we're going to assume that the charge on all of our ions is +1. Sometimes that's not always the case, so we'll just write here, if the charge Z is +1, then the parent peak is the mass of your molecule. So again, this is super useful because we can figure out the mass of our molecule, and that can help to narrow down what our molecule is. Now, if we look at methane, the molar mass of methane is about 16, so that works out. Now, you might be wondering what some of these other peaks are. We have one at 15, 14, 13, 12. Those are due to fragmentation of methane. So methane can lose hydrogen atoms, and that's just due to that beam of electrons hitting it. So it's kind of similar to how our radical cation split apart and formed a carbocation and a radical. So we could lose hydrogens off of carbon in methane, and that's going to decrease the mass by 1 for every hydrogen that we lose. So if we lose one hydrogen, the mass is 15. If we lose another hydrogen, the mass is 14, and that will continue. Now, you might also be wondering, what is the little peak to the right of our parent peak? So that is due to isotopes. So remember, carbon has multiple isotopes. The most common one is carbon-12, but there's also carbon-13, which is the next most abundant isotope. So we could potentially have some of the methane molecules here with carbon-13, and that's going to increase the mass by 1, but it's such a small amount that we get this tiny little peak just right next to the parent peak. Again, that's just due to carbon-13. So that's kind of cool that mass spectrometers can detect isotopes as well as fragments of a molecule. All right, so let's try analyzing another spectrum. So this is a mass spectrum of pentane, and let's look at, or let's try to find the parent peak. Oh, I can't spell today. Parent peak, not pack. So see if you can figure out where the parent peak is on this mass spectrum. Okay, so remember we said that the parent peak will be the tallest peak in the rightmost cluster. So if we go all the way to the right, we see this cluster of peaks here, and the tallest peak is that one. So it looks like that's at 71, 72. Okay, so the mass to charge ratio, or the mass of our molecule, is 72. Let's see if that makes sense with pentane. So pentane has 1, 2, 3, 4, 5 carbons. And how many hydrogens? Let's see. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so if we add those all up, let's see. So we have 5 carbons, which have a mass of about 12, plus 12 hydrogens, which have a mass of about 1. Okay, so what does that give us? Let's see. I'm going to plug it into my calculator. Times 5 plus... Yeah, that gives me 72.17 as my mass for pentane. And so that is really close. Great. So if I didn't know what my molecule was, at least now I would know that its mass is 72. Okay. So now let's look at these other clusters in the mass spectrum. Now, you might notice that this peak in the middle is our tallest peak overall. So the tallest peak in your mass spectrum we call the base peak. So this is the most abundant ion in your sample. And this could be due to fragmentation as well. So maybe a piece of your molecule split apart or separated due to that beam of electrons. But what's great about that is we can kind of use that to figure out, okay, what exactly broke off of my molecule, and can I kind of piece together all of the fragments to figure out what my original molecule was. So one way to figure that out, let's see, so this peak, this tallest peak, is at 43. So let's take the difference between 72 and 43. What is the difference? $29. Okay, so let's look at the possible fragments that we could have from pentane. Well, we could lose, let's see, a methyl group. Okay, so if we lost a methyl group and it just was kind of hanging out on its own, what is the mass of that methyl group? So 1 carbon plus 3 hydrogens would equal 15. Okay, what if we lost an ethyl group? What would the mass be for that ethyl group fragment? So 2 carbons plus 5 hydrogens equals 29. Okay, so it looks like this change in mass of 29 is due to the loss of an ethyl group. Okay, now what about this peak kind of down here? That's also a pretty tall peak. That's at about, let's see, this is 55, 56, 57. Okay, what's the difference between 57 and 72. 15. So that would be due to the loss of a methyl group. All right. So if we didn't know what our molecule was, we would at least know that we do have an ethyl group and a methyl group. That's part of our molecule. And we could keep going. We could look at maybe this peak over here. That's at about 27. There's also one here at 29. And then there's one down here at 15, so that would be our methyl group as well. This 29 peak would be an ethyl group. And then we would also take into account that the mass of our molecule is 72. So we would want to kind of figure out, okay, I'm getting all of these ethyl and methyl losses or fragments, and how would those all add up to 72? Now, let's go over some more tips that we can use to figure out what our molecule is, because even though this gives us a lot to start with, there's some other things we can use as well to kind of piece together our molecule. So one tip has to do with whether your mass is even or odd. So we just saw that the mass of pentane is about 72. Let's look at a molecule that contains one nitrogen. So this has a mass of 73, which is really close to 72. And then let's look at a molecule that has two nitrogens. This has a mass of 74, so that's also really close. So if you have an even numbered mass or mass to charge ratio, then you likely have a molecule without nitrogens or an even number of nitrogens. So let's write that down. An even numbered mass or mass to charge ratio means you have a hydrocarbon, so just carbons and hydrogens, or an even number of nitrogens. So if we didn't know what our molecule was, we could say, okay, the mass is even. So either I have just carbons and hydrogens, or I have two nitrogens, or maybe 4 or 6, so an even number of nitrogens. Now, if you have an odd numbered mass, that most likely means that you have one nitrogen or an odd number of nitrogens, so 1, 3, 5, etc. So this is actually called the nitrogen rule. So I'll just write that up above, the nitrogen rule. So this is kind of a cool rule because if you do have an odd numbered mass, right away you could guess that you might have a nitrogen in your molecule. And most of the molecules that we'll be analyzing have either carbons, oxygens, nitrogens, and hydrogens. So some combination of those. So it's always good to double check if you have a nitrogen. All right. So now let's talk about that M+1 peak. So the peak that's due to the isotope, carbon-13. Now this could occur for other atoms as well. So let's just write that the M+1 peak is due to heavy isotopes. So remember we saw that cluster of peaks, and then there was a little baby peak next to the tallest peak. That was our peak due to isotopes, which is the M+1 peak. And then it's still considered a radical cation. All right, so let's write out some isotopes that will be pretty common in our molecules. So we have carbon-12, carbon-13, and then there's also carbon-14. All of our molecules will have hydrogens, so remember there are two isotopes for hydrogen, hydrogen 1 and hydrogen 2. And another common element that we'll find in our molecules is oxygen. So there is the oxygen 16 isotope and an oxygen 17 isotope. All right, so let's look at the abundance of these isotopes. So out in nature, carbon-12 is the most abundant isotope for carbon. So it's present at about 98.9%. Carbon-13 is present at about 1.1%. And carbon-14, there's really only trace amounts of carbon-14 in nature. Hydrogen 1 is present at about 99.96%. Hydrogen 2 is present at only about 0.01%. Let's see, the natural abundance of oxygen 16 is 99.96%. and oxygen 17 is 0.01%. So if this all runs through a mass spectrometer, we would be able to see a carbon-13 peak because it's abundant enough to see it. But these other isotopes are not abundant enough to show up on a mass spectrum. So those are too small to see. Sad face. Okay. So one advantage to carbon-13 is because we can see it on a mass spectrum, we can actually use it to figure out how many carbons we have in our compound. So I'm actually going to erase these other isotopes here so I can kind of show you how we can use carbon-13 to our advantage. All right, so how we would do this is the number of carbons in our compound will be equal to the M+1 peak intensity So on the mass spectrum, how tall is that peak? So it might be like 1.1%, maybe 2.2%, depending. And then we're going to divide that by the intensity of our parent peak, the M peak. Then we're going to divide that whole thing by 1.1. which is the ratio of carbon-13, or the abundance of carbon-13. And then we'll just multiply all of that by 100. Okay, so let's look at an example of how this equation would work. Okay, so let's say we have a parent ion with a mass to charge ratio equal to 68, and its relative intensity on the mass spectrum is equal to 100%. And then let's say we have our M+1 peak, and that has a mass to charge ratio equal to 69, so it's right next to the parent peak. And its relative intensity is equal to 4.3%. So let's figure out how many carbons does the compound have. Okay, so let's use our equation that we wrote out on the last slide. So we're going to take that M+1 peak and its intensity, divide that by the intensity of the parent peak, multiply that by 100, and divide by 1.1. So if you want to pause the video and try this on your own first, you can. And then when you're done, you can unpause and we'll go over it together. Okay, so let's figure out how many carbons this compound would have. All right, so my M+1 intensity is 4.3. And then I'll divide that by the intensity of my parent peak, which is 100. Then I'm going to divide that by 1.1 and multiply by 100. Okay, so that gives me approximately a value of 4. So that means that my compound has 4 carbons. So this is a super useful tool, and typically the mass spectrum that you have is going to come with the relative abundance data as well. So you can use that to your advantage to figure out how many carbons your molecule has. Okay, so far we've learned a few different tools we can use to try to identify what our unknown compound is. In the next video, we're going to dive a little bit deeper and we'll look at some more examples of how to figure out what your original molecule looks like. So I will see you then.